For this activity on series and parallel circuits, you will need a 9-volt battery, 2 light bulbs from Christmas lights or something like that, a whole bunch of strips of aluminum foil, and some Scotch tape. Let's begin with series circuits. So series circuits are ones in which there is only one path for the current to flow. And so you have a circuit something like this, where you have a battery, that's the symbol for a battery, a long and a short parallel line. And you have some wire, which is what this represents. And here we have a resistor. And in our case, we will use a light bulb, but a resistor is a good stand-in for just about any load on a circuit. And so you'll note that there's only one way for the current to flow. There's nowhere else that current can go. It has one path back to the battery, and that's it. And that is the idea behind a series circuit. And why it's called that is because everything's in line, everything's in series with each other. So if we put in another, say, resistor, or 2 light bulbs, then we have something like this, where the current flows like so through both and then back to the battery. We'll call that R1 and R2. And again, those could be anything. In our case, we will use some light bulbs. And so because there's only one path for the current to take in any series circuit, then the current that is out of the battery, we'll call that I.O., is equal to the current everywhere. And so if we have 1 and 2, if we want to know the current at 1, the current at 2, it's really the same for them all. And if we could have 10 things in this series circuit, it would be the same everywhere. It's one path, that's it. Something you should really appreciate about current in an electrical circuit is that it's not like a fire hose where all of a sudden the electrons fire out of this battery and then reach this resistor, slow down maybe, and then shoot over, and then reach this resistor, and then shoot back to the battery. It's not like that. All of the electrons in this circuit all feel the field once that's connected, and then they all move at the same time under the same influence. Sort of like if you had multiple balls on a ramp at various heights and then let them go, well, they would all start rolling at the same time. So it's not like this, it comes out of here like your water hose and then gets to the end of the hose over here, and that's got to go through a few things. Because some students like to ask, well, how does the electrons here know that there's 2 resistors here? Well, it knows it the same way the rest do, in that it's feeling the field here. And so it's being pushed around the same way this one here or that one there is being pulled by the field. They all are feeling that field independently, in the field from each other, of course. But it's not like a fire hose that way. So sometimes the plumbing analogy gets used, but it's not always the best one for what's going on here. But having said that, the current is the same everywhere in any series circuit. And so if we wanted to look at something else here, we'll go through all 3 things in Ohm's law. V equals IR. This is how we solve circuits. We look to see if we know the resistance and we know the voltage, we can find the current. Or if we know the current and the voltage, we find the resistance. Often, though, the resistance is one of those things you would read off of a package or something like that. It's really the current that changes the most in a lot of these circuits. Voltage is generally, again, set by the power source. Resistance is set by the resistors themselves, their manufacturing, and so the current is the thing that often changes. But you may only know 1 or 2 of those things in various spots, and you have to figure the rest of them out. So if we wanted to know voltage, then the voltage out of the battery, or the total here, the original voltage, VO, is that of the source. And so in our case, it's going to be a 9-volt battery, but it could be any battery that you use, 6 volt, 1.5, 10,000 volts, whatever. That's the power source voltage. And what we find then in a series circuit is the voltage being carried by charge here, so that means it has energy. That charge has energy. Voltage potential difference is really like lifting a rock in a gravity field up to the top of a cliff. So voltage, again, is sort of like the height of a cliff and a cliff together, but there's no energy there unless you put a rock. So it's this charge that has the energy. And so once it reaches this resistor, it gives it all to the resistor and then back to zero here, which is where it's going. And it's like hits the ground. And so it would all get it there. But in the case of two resistors, well, 9 volts, 9 volts, 9 volts, it can't possibly use all the energy with this one, because then there'd be none left. This would be like rolling on the ground now. Well, how are you going to spin a wheel if you're supposed to be rolling down a hill or something like that, or water on a waterfall, so on and so forth. So in this case, it gets split. And if they're both equal resistors, then the voltage would be divided evenly. So 4.5, 4.5 in this example. But it could be, if these resistors were different, 8 and 1, 7 and 2, so on and so forth, but it cannot add up to more than the voltage from the power source. So we write a law like so. These are Kirchhoff's laws. And so they just all add up to the total. When there's only one, then they got to be the same. And then lastly, when we want to look at the total resistance, and I'll call this RS to note that it's resistors in series, because there is a different rule for resistors in parallel. Sometimes this is RT, just total, which is fine too. But for series, you have to add them up. So if this was 5 ohms, then great, that's it. There's just the one, 5 ohms. But in this case, if this was 5 ohms and that was 5 ohms, your total would be 10 ohms. So you basically just take all the ones you have in a series. You could have 10 in a row, and you treat them like the voltages. You simply add them up. There was a third one, so on and so forth. So those are called Kirchhoff's laws for series circuits and how they work. So let's try building a series circuit now. We'll start with a 9-volt battery, and we'll put that here. We'll try to build this one here. So 9 volts there. And then I've taken my strips of aluminum foil and sort of bent them into this shape here so that they can look like the wires as we have them in on our diagram. But of course they can go in any direction that you'd like, as long as they connect to the battery and to the light bulb. So there's my second set of wire. And so I'm going to take my battery and I'm going to put the positive side where I had it in the picture. I think it doesn't actually matter, but I'm going to put that down so it looks the same. And be careful that that battery does not have a short in it, meaning that there's some space. You notice that I had some paper in between. You do not want to do this, because then you make a short circuit. You want to always keep those separate. So I'm going to keep that like that. And now think about this. That knob on the end was at plus 9 volts and the other one was at 0, to have a potential difference of 9 volts in total. That means this entire conductor here is now at 9 volts and this one is at 0. And so all we need to do is put something that can use that energy in between. And so let that charge flow through. The charge this is essentially like now falling off the cliff, and that energy is converted into light. And we'll see that right now. We should be able to put that down. And there we go. Now, I'm not going to leave that connected for very long because they get very hot and they can burn out. So don't do that. But you saw it there now, that a series circuit is able to produce the light quite bright. And I'm going to fold this over. And again, the shape doesn't really matter as long as all the metal's touching itself, so that we have a complete circuit. I'm going to take this another piece of tinfoil. I could wire 2 light bulbs together, but I wanted to make it look like this. So I'm going to build that circuit next. And I'll put in my first light bulb, which should do nothing because there's still a break here in this circuit, so nothing's getting back to the battery. And then when I put the second one in, now think about this. Up to here on this side is 9 volts, on this side 0. So now that I have 2 lights in here, you should notice that they look a little dimmer this time. We have both of them on. but they don't look as bright as when there was only one. I'm going to take them off so again they don't burn out. So you should never leave those connected like that. But what we had here was this situation, and we saw that they were dimmer because, as we said, the voltage gets split between the two. It's 9 and 0, and so each of these, assuming these resistors are basically the same, we get 4.5 and 4.5. And so if you're only getting 4.5 volts with your charge, you're not getting as much energy. It's like only falling halfway down the cliff and then falling the other halfway down. And so those light bulbs are a lot dimmer. Okay, next we're going to talk about parallel circuits. So parallel. These are still going to, the ones we're going to make here are still involve a 9-volt battery. So we'll draw that. Plus side, minus side. There's our battery. And we'll have some wire, some conductor, some tinfoil going to a light bulb, and then back to the battery. So that might look familiar. That looks like our first scenario for our series circuit. But instead of putting another light bulb in series, we're going to put it in parallel. So we see when we draw these that they're in parallel lines to each other, so we call it parallel. So we're still going to use the 9-volt battery. We're going to use the same 2 light bulbs, and we're going to use potentially the exact same tinfoil plus a little bit more to get here, but we'll see some of the differences with that. So here's the major difference for parallel circuits versus series circuits, is that the current has 2 choices here. It can flow this way to get back to the battery, or it can flow this way to go back to the battery. It has 2 choices here. It can go this way or that way. In series, there's never a choice. There's only one way for it to go. We said, according to Kirchhoff's laws, that the current is the same everywhere. And so in this branch, the current is the same everywhere. I should say there, where it doesn't split. And in this branch, it's the same everywhere. So you'll note that the current here comes out full blast, let's say, even though it's not coming out. We just talked about that. Out of there, they all know this at the same time, but essentially what happens here is the electrons that have 9 volts have a choice. They can go this way, we'll call that I1, or they can go this way, we'll call that I2, and we'll say coming out of the battery is IO. So there are 2 paths for the current to take in this case, which means that this and this and this cannot all be the same. They must divide up. And so our first law here for parallel circuits is that in any branch, and what I mean by branch is where you have a situation here where it has a choice, so here's one branch and then it reconnects, and here's the other branch and then it reconnects, that in each branch, not necessarily, you could have more resistors in it. I could put a resistor here and a resistor here. The current would be the same for all 3 of them, but you would have to treat those ones like they're in series. But either way, for each branch, you go together, that should add up to the total. So you can't get more than the total that's coming out of the battery, but when they recombine here, this is sort of where the water analogy is better, so that if a river was flowing here and a little stream broke off and some of it kept going, if they reconnected again, well, you'd get all the water back, and so you'd be back to IO. So you can add those all up. Another thing then, if we wanted to know what kind of voltage we have at each of these resistors, we'll call this one R1 and we'll call this one R2. The voltage then coming out of this battery, or the voltage that this battery has, the potential difference between here and here, we want to know, well, how much of it does this one get and how much of it does that one get? And we saw when they were in series that they had to divide it up somehow so that it added up to the total. But in this case, because it's the charge that carries the voltage here and that energy, when the charge, which is in the current, it's the electrons flowing, some of them go this way and some of them go that way. And so no electron goes through both. They either go this way and then back, or they go this way and then they're back. And so the voltage then, which is carried by those electrons, carried by the charge, it's the rock that's falling down the cliff or whatever, it only passes through one thing. And so for each branch then, similar to the current before, is going to be the same. And so 9 volts to this guy back to the battery, 9 volts to that resistor back to the battery. And again, you can do this 100 times, a million times out, and they would all get the full 9 volts of the battery. Because you got to remember, the voltage isn't the full energy. It's just a way of expressing how much energy the charge could have. That's why it's called potential. And so if some charge goes this way, well, that some charge has the 9 volts, and some charge goes through this one, it's got the 9 volts too, so on and so forth as you go. And of course, if there was more resistors in this branch, then it would divide up the way it does in series, and we will do some examples of that when we get into the worksheets. And lastly, and this is the one that students do not like, is how resistors add up in a parallel circuit. Now, you might think, okay, well, two resistors in parallel, well, that's got to be worse than one, so it's got to add up to be even more resistance the more you add. Turns out it doesn't. This is like having 2 doors to get out of a classroom, right? A crowded classroom. Both of them are going to clog up people, but if you got 2 to get through, well, then the overall resistance, let's say, out of the room has dropped. And so, in fact, for parallel, the rule is 1 over R1 plus 1 over R2. And again, these are the branches, all the resistors in that branch, so on and so forth. So as many as you have, or as many branches as you have, then you add them up this way. So it's 1 over, which actually means that if this was the same, which we're going to build in a second here, the resistance, the total resistance in this circuit is less than the total resistance in the series circuit that we made with 2 resistors in it. So let's try building this one. We'll start with our 9-volt battery again. I'll put that here, try to use some of the white space. And we'll make this first branch the same way we did before. I'll put one of those and one of these. Similar thing, so again, I can get my everything to touch. And then I'm going to need some extra room here. And again, this doesn't matter that that's overlapping. I just need it to touch. So there's one branch where it'll break off. There's the other place where it can flow. I'll take another piece of tin foil. And we'll do something similar. And this may be where you would want to use your Scotch tape if you had that out. I'm not going to bother, but just to make sure that's all touching, that doesn't matter that that's sticking out. And so I will set this up so that one side has the full 9 volts. You see how the 9 volts makes it to both sides, and then the 0 volts on that side. And again, that's all connected to there. And then I can put my first light bulb in. And I'll try not to leave it too long because I don't want it to burn out. There it is. It's lit up the way it was before. And then we'll see when I put this one on that they don't dim. They're actually quite a bit brighter than they were when they were in series, and that's because the full 9 volts gets to this guy, and the full 9 volts gets to that light bulb as well, because the current has been split there. I want you to think about what that means about the current difference between a series circuit with 2 light bulbs in it and a parallel circuit with 2 light bulbs in it. There's got to be something different here in order for them to both light up as if there were only 1 light bulb in the circuit. But nonetheless, there is some differences here. And I'm not going to leave these on, but notice too, if I take this one off, that one doesn't go out because it still has a path to go. So this is how you know the difference between your cheap Christmas lights and the expensive ones is the cheap ones are in series. So one goes out, it breaks the circuit, that's all done. But in parallel, meaning one can go out and the other stay on. And again, that's probably how your house is wired too, since you know that when you turn off the light in one room, they don't all go out in the rest of the house.